So I'll not go through the worked example. I hope that you have done it. And now I'm jumping onto the self-testing question, and it is quite easy. I don't think I'll take 2 hours today to do all those to finish this off. All right, so for question 1, already is given a thin layer chromatography. Let me take the pen first so that I can write. Okay. Oh, it's too thick. Oh. So anyway, it is thick, but to do a thin layer chromatography, TLC. What is the TLC is made of? Can anybody tell me what is TLC is made of? Paper and Erlin, do you want to try? What is thin layer chromatography is made of? Chelsea? Noor Farah? Alumina. Lynn said alumina. Noor Farah, want to try? Sorry?
Solvent.
Oven?
Solvent.
Yeah. Solvent, but solvent is the liquid, the solid phase, and stationary phase. I'm saying the stationary phase. What is made of? Bilal said paper already. Okay. Vanessa, Brenda. Thin layer chromatography means TLC means thin layer chromatography. Thin layer chromatography comes from the term this is a very thin layer of alumina or cellulose is made on the surface of a plastic. There is paper chromatography and then there is thin layer chromatography. Thin layer chromatography is not, the stationary phase is not made of paper. It is made of a thin plastic polymer, all right? A polymer, something like polymer sheet. It's made of polymer sheet, but the polymer sheet, on the surface of the polymer sheet is covered with alumina or the cellulose, alumina or cellulose, a very fine, thin layer, very, very thin layer, like hair, less than a hair thickness. All right. And then that is put into the solvent. So that is why it is thin layer chromatography, we call it. So thin layer chromatography was done. The polar stationary phase was silica gel. Yeah, silica gel as well. Silica gel, then alumina, and also polymer. Sorry, not polymer. What? Cellulose. All these things are used. A ruler was then placed next to the plate, and then it shows that we started from here. We started from here, and then it reached until this part, right? So what is the RF value? RF value means RF. What is RF? Yeah, I forgot. What is the? What does it mean? RF value means? Can anybody tell me what does it mean? RF value. Retention factor, right? Okay, so this thing, I mean, we started here at 2, it's not at 0, yeah? And then it reached until 16. So now we see that hold on. Now we see that we started at 2. Excuse me. We started at 2, and then the solvent front, where is the solvent front? We need to find out the solvent front first. Only then we can find the retention factor. So solvent front until 20. This is the solvent front. So we started at 2, not at 0. So 820 minus 2 is 18. Solvent front reached until 18 units. And then this reached to 2 minus 16 is 14. All right. So this is means that probably 0.78, right? Yeah. So this is how we get the. This is how we get the what do you call it, retention factor for this. A student used paper chromatography to separate two components, right? Paper chromatography, it was TLC, but let's say that X and Y. The student used X and Y. For this, I'm going for the question number 2, okay? Question number 1 is done. X and Y, and a spot of the solution was initially placed at the origin. When the spot corresponds to X, X goes somewhere, advanced to 4 centimeter, had advanced to 4 centimeter, and the the X goes to somewhere which was there, but it advances to 4 centimeter. We don't know whether it started at 0 or it started at 2 or it started at 4, wherever, but it goes to 4. I mean 4 units it reaches, and by that way the retention factor was 0.5, 0.5, right? If the retention factor is 0.5 and we know that it advances to 4 units, so can we find the origin? We can, because the retention factor means how much it advances and how much originally the solvent advances. So now if we divide this 4 over this 0.5, because RF is 0.5, it says 0.5, so that which is equal to whatever it advances, X advances over the solvent front, SF. Okay, so it is 4, X advances is equal to 4, and then if I replace or rearrange this equation and bring this 5 here, we get the solvent front is equal to 8. Now solvent front is equal to 8. We find out that solvent reaches to 8, but for X only reaches until 4. So Y, it says that the Y component was 1 centimeter behind. If it is 1 centimeter behind from X, X reaches to 4, Y is 1 centimeter behind, so it should be 3, isn't it? So Y should be at 3, since it is 1 centimeter behind from that of X, so it is 3. And I know that the solvent front is 8, so 3 over 8 will give us the answer. I'm not sure what 3 over 8 should be. 0.375, so it's very close to 0.38. Question number 3 says that the 2 different food dye samples W, Z, Z were compared using thin layer chromatography as shown below. Which of the following statement is incorrect? Z is more strongly adsorbed to stationary phase than W, and Z has a lower RF value, right? So Z is staying here where W reaches until this far. If we say that, okay, this is 0 centimeter, maybe this is 1 centimeter, this is 2 centimeter, so this way. So W increases or traveled upward, but Z stayed there around 2, right? So Z is more strongly adsorbed to stationary phase, Yeah, isn't it? It's true. Z is more strongly attached and it has lower RF value because the solvent front is here. It is solvent front. Oh, it's written already. Z, option B was Z was more strongly adsorbed to the stationary phase than W, and Z has higher RF value. It is not true. Half of it is true, but this part is not true. So this is, cannot be a correct answer. W is more strongly adsorbed. It is not. It is not absorbed to the stationary phase, and that is why it reached upward or go up. So that is why these are not, but A is only the correct answer. 4. Question number 4. Consider the following thin layer chromatography plate of compound ABC developed using suitable mobile phase on a polar stationary phase. Polar stationary phase. Polar stationary phase. So that means like dissolves like. Why this becomes like, I don't know why it looks like it's not clear. But okay, this is solvent front. This is the origin at 0. And the first one, this is the first A, sorry, it's not first. The A reaches until 3.5 centimeter, B reaches to 5 centimeter, and C reaches to 8 centimeter, right? The RF value of the least polar component, least polar component. If the mobile phase is, mobile phase, there no information about the mobile phase, but the stationary phase was polar. Stationary phase is polar, means it will attract or it will bind the more polar things on it. All right, it will bind more polar things on it. So the least polar will, of course, will not be strongly bonded to this stationary phase. So that one will travel up. So C is the most or least polar or most unpolar, so that it goes up. And that is why 8/10 should be 0.8. 5. Question number 5, it says that three components P, Q, and R of a mixture were separated using thin layer chromatography. The results are shown below. The same components, okay, first of all, again, 3 components P, Q, R of a mixture was separated thin layer chromatography on a mixture. It is not shown which one is what, right? Whether the phase is polar or non-polar or whatever, it is not given, but it is just given that, okay, on the same, on a plate, thin layer chromatography, TLC, PQR 3 components were separated and it looks like that. So P is the most stick to that stationary phase. That means it has the lowest RF, right? It has the lowest RF, retention factor. And then this is the second lowest, RF2. And this is the highest, that's RF3 or RFH. This is the highest. If we do the same thing using a column chromatography, right? The column chromatography, if we do, and you know, this is the column chromatography. This is a valve here to stop this thing. So which one? Let's say that is the column chromatography. So P, which one will be where? The farthest gone down, will it be the Q or will it be the R or will it be the P? That is the thing we have to understand. Since PQR is the P is more stick to that. That means it does not have the um, higher retention factor. So in the column chromatography, Q will be the lowest. That means it is going up. That means it is going farthest, right? It is going farthest. Correctly state the order of increasing retention. Increasing retention time for this. So P will be the highest retention time. Highest retention time P, and then there will be R, and then there will be Q. So Q will be lower than R, and R will be lower than P by this way. So D is the correct answer for this. Question number 6.
Sir,
Yeah.
can you explain question 4 again? Can you explain question 4 again?
Yeah. I'm here. So 3 components, PQR.
No, question 4.
Question 4.
Yeah.
Okay. So here it is this phase is polar, right? It's a polar stationary phase. And from the lecture slide, we have seen like dissolves like. Like if it is polar, it will dissolve the polar thing. If the solvent is polar, it will dissolve the polar things. If the solvent is non-polar, it will dissolve the non-polar thing. And same thing goes with the stationary phase as well. If this stationary phase is polar, it will attract the polar components. If the stationary phase is non-polar, it will attract the non-polar component on it. So which one is the least polar? That means the most unpolar material or component on it. Since the plate is polar, the stationary phase, or let's say this is the stationary phase, it is polar. So if I put the polar thing here, or one component polar, let's say A, B, or C, I put A is very polar here, so A will stick to this. It won't try to, or it won't move, because it got its best friend there, so it won't move anywhere. But if I put one non-polar, that is which it does not stick or like the stationary phase, it will try to be not very stable. It will try to move up. Consider in water, you put 1 drop of oil, any oil. What will happen? The oil is there, it does not mix, and it is very easy to move around that oil, right? A small droplet, it will cause, make a small drop and then it will be there. So it doesn't stick anywhere, it can move. You can even blow it like this, and then it will move around in that water. You can try in a glass of water. But if you, in water, if you put 1 drop of the alcohol, or even this hand sanitizer, it has a lot of alcohol, right? Different type of alcohol, but alcohol. So if you put 1 drop of hand sanitizer, and immediately it vanish. You cannot distinguish. So because the alcohol is polar, so it will go in the water. Water is a polar, but oil is non-polar, and then water is polar, so they do not mix together. So that is why I'm saying that B is least polar. So it does not stick to this, or it does not stick strongly to this polar stationary phase, and that is why it moves upward. It moves further, right? And another another principle for this thin layer chromatography, TLC and paper chromatography is if this stationary phase is polar. If it is polar, the solvent must be non-polar. It should be non-polar, or vice versa. If it is non-polar, stationary phase, then the solvent must be polar. So this is the vice versa thing actually. Okay, is that okay now?
Thank you, sir.
Okay, so question number 6, we are going burette packed with finely divided alumina powder, all right, was used to separate the component in a plant extract by chromatography. Like in a plant, there are many things, right? Chlorophyll, xanthophyll, then carotene, so many things we have in the plant extract. So we want to find, get a nice, beautiful separation of the component, just like yesterday we saw in the lab that it separated different color and gives a different band. So what we do is we try to extract it, and it is the alumina, and put the plant extract, and then we put some water inside so that it goes down. So what will happen is, which of the following statement is incorrect? Now we get separated. We do not know what is A, B, C, but just coded it with A, B, and C, different things, 3 different things in the plant extract. Remember that I put water to bring the component down to get separated, right? So water is the polar, right? What is the polar solution? So it will bring down which one is the most polar thing faster, right? It will bring down the most polar thing faster with it. So C comes farther. So C should be more polar than B, then A. And C is not strongly bound to this alumina. If it were strongly bound, then it would not move, but it moved from here and down to here, right? The C came down because all of them, A, B, C all together we started here. We started here, A, B, C all together, and then C came further. That means C traveled more. It did not stick strongly. But A is more strongly attached to this alumina, then B, then the least is C. So from all these, we see that answer option A is the correct answer, because it says that A is more strongly. Oh, sorry, this is correct answer. He says that which is incorrect. Which is incorrect. That means A is more strongly absorbed. That is correct. Extract B has a longer retention time than extract A. This is incorrect. Where is it? Oh. Okay, so extract B has longer retention time than extract A. It is incorrect because B, it does not have a higher retention, right? Because it has a lower shorter retention time. Retention time is A retained there higher or more, or A stayed in this process longer time. So what will happen is, if let's say that I give 10 milliliter water, so I get this separation. I get another 10 milliliter water, and then I wait for another 5 minutes. What will happen is C will come down to here, B will come down to here, A will come down to here. So I add another 5 milliliter, 10 milliliter water, I wait another 10 minutes. So what will happen is C will go out, C will elute, and then B will come down here and A will come. So that means A is staying longer than any one of them. So A has longer retention time here, right? So this is so the options say that extract B has longer retention time. No, this is incorrect because just now what I said that A has the longest retention time here for this. Question 7 says the picture below shows the chromatographic separation of a 3-component mixture on a silica gel column, all right, polar, with a non-polar mobile phase. Which of the following statement is incorrect? So when it is in a MCQ question for you guys during the mid-sem test or test 1 or final test, please read the question first. Sometimes it's incorrect, sometimes it's correct. So if it is incorrect and you did not read it properly, you say you thought it's correct and then you made a mistake. So don't make that mistake, okay? Which of the following statement is incorrect? Now, this is a polar stationary phase, and the mobile phase, the water, is non-polar. So C, no, not C, the green one is coming further down, is almost washed with this solvent. That's why it is coming down. So if it is coming down, then this green is more polar or non-polar? Green is more non-polar, right? Because the mobile phase is non-polar and this green is coming along with the mobile phase. Mobile phase is coming down, is going out from the tube. The mobile phase is going out from this column or from this tube, so that it is a mobile phase. I mean, it is a going out, washed out. So that is why it is non-mobile and is non-polar, most non-polar. So what are the options here is given, like on component 3 is the least polar among the 3 components. Yes, that is correct. This is what I just explained. Component 1 will have the smallest RF values. That is also correct. Okay, so this is the I is the smallest but lower, or smallest but higher retention. Smallest but higher retention. Smallest in value RF, but higher in time. Higher time or longer time, it will stay there. So this is also correct. But for C, it says that component 2 adsorbs stronger to silica gel than component 1. No, it is not. Component 2 is actually, this one is less strongly stick to the silica gel. That is why it is washed out faster than the blue one or number 1. So that is why it is the incorrect. So it is the correct answer for here. Question number 8. Petrol is a mixture of hydrocarbon, nucleus, which are volatile in nature. Forensic investigation suspect that traces of a substance found at a suspicious fire could be petrol that was used to start the fire. Which of the following techniques could best be used to identify the substance? So It was a hypothesis that probably petrol was used to set the fire up, by which way, or there are a trace amount of the substance is left, and we suspect it's petrol, which will be the better option to find out what was the cause. Thin layer chromatography. Thin layer chromatography is this is the thin layer chromatography, right? Where is it? Just now there was a photo of thin layer chromatography. So you know what is the thin layer chromatography looks like. Come on, now I cannot find. Okay, so this is the thin layer chromatography. You put it in a beaker, and then you put it on thin layer chromatography and TLC. Paper chromatography, almost similar. Thin layer chromatography. In a beaker, there is a thin the plastic coated with alumina or cellulose, and it is inside a solvent. So if it is a petrol, if I put it here, what will happen? Let's say I put it here. This is the origin line. I put it here and then I put it inside the solution. So what will happen? It will vaporize. It will escape into the air. It will not move up. It will escape because petrol is volatile, so it will just evaporate up. So same for the paper chromatography. So paper chromatography, a thin layer chromatography is not an option. UV visible spectroscopy we haven't studied yet, so it's not. AAS we haven't. So gas liquid chromatography is the best choice for it that we can find out. If we want to do some forensic investigation, gas liquid chromatography would be a good idea to do this, to find out whether it was petrol or not. Why? Because petrol is, volatile, and in gas liquid chromatography, we need the sample to be volatile so that the gas can carry it through this column. And petrol is better that it is readily volatile, so we don't have to use much effort to make it volatile. Okay, question number 9. Which of the following analysis is not suitable to be analyzed by gas chromatography? Percentage of methane in natural gas, yes, can. Just now we have seen it. It can be, but it says not. Percent of vinyl chloride in air can be. We can use it. Percentage of sugar in a can of cola. You see the sucrose and fructose and all those things in the sugar. And another option is D, ethanol in petrol. Ethanol is also volatile, vinyl chloride volatile, methane in natural gas is volatile, but sugar is not volatile, right? It is not volatile. It's a quite bigger molecule, and then you need to, you have to make it burned in high temperature and make it volatile. But if you burn in that temperature, it is going to be disgenerated, and then it from sugar to become something else if we put too much high temperature. So this is the correct answer because we cannot find the percentage. So what should we use to find it? HPLC. HPLC we should be used. High performance liquid chromatography that we have studied yesterday or on Monday. Question number 10 says that the concentration of a substance is most accurately determined in HPLC by measuring the peak area. So this is how this GC and HPLC both actually detects or gives us the result in a form of wave. This GC, this HPLC, this paper chromatography or TLC, they are not human. They are not dogs. They don't sniff. or find out, okay, it smell like petrol, it tastes like sugar. No, they don't know, they are machine. So they communicate us, or what they give us is signal, right? They give us signal and in a form of wave. So for HPLC and, oh my God, for HPLC and GC is almost similar. So like this, they will give us this type of, sometimes like this, sometimes like this and this. So this is how they tell us that they have sensed something at this, like say like this is time, is time 1, it's time 1, it's time 2, it's time 3, it's time 4, and so on. And this is the peak height. Peak height is millimeter per millimeter or centimeter, whatever. So, right. So this is T1 means 5 minutes, 10 minutes, 20 minutes, whatever. So this is the peak height. This is the peak height, and peak area is the area underneath one peak. The area underneath the peak. Okay, so this is the area underneath this peak, or if I take this, this is the area of this, and then the whole area under this peak. This is the area, whole area under this peak. So we can consider these two different things: the under the area underneath the peak, or the height of the peak. Sometimes we will see that some peaks are like this, very sharp, like a needle, very sharp. All right, and it is very good. All right, this is X, this is Y axis. Okay, and this is very good. This tells us the how pure or how unadulterated a component is there. But when we get an area under this peak, right? Under this peak, when we get some area, it tells us that how much of that same component, let's say that component X, right? Not X, maybe component A. How much of component A is in that sample? All right, this is area. The bigger the area, the higher the chances of component A. But there is some other consideration. But for us, we will just consider this is true now. OK, there are many other considerations we need to. I mean, if you go higher classes, you will learn, or if you go do research, you will learn more about it. But simply, if we the area is peak area is better to consider if we know that this peak is for component A. Sometimes if the area is like this, okay, the bigger the fat area that I just draw like this, it means that many component inside together. It's not a single component, maybe. So that is another consideration. So we have to be sure that it is only one component. So that's why I'm saying that if you go higher classes, you will learn more. But retention time, no, retention time only gives us the retention time only gives us the identity of the component in regard to the standard components that we will be using. We have to do the standard run. Standard run means I want to see it is coming. Next question, I think it is coming. But let's say that I want to see A if there is component A in my sample, or let's say I want to see whether there is tannin in my tea. Do I have tannin in my tea? So what I'll do is I will run a standard tannins, only tannin. There is nothing in that standard, only tannin. I will run at the same temperature, same condition, same instrument, same column, and then I will run my T sample to find if my T has tannin. So if I have only tannin, right, standard, I will get a peak like this because there is only tannin. And this is, let's say, TX. And on the same instrument, same temperature, same condition, I draw my T, sample of my T, and then I got a small peak at this TX. So now I'm sure, I'm confirmed that I have tannin. And of course, other peaks will come, as well, because T has many other components. So that is why, okay, enough talking, I think. So peak area is more appropriate. Peak height also gives us an idea of how much this sample can be, but mostly it will give us how pure our sample is. Then the concentration. Concentration comes mostly, we have to consider peak area. Oh, okay. Question number 11, sorry. It says that a retention time can be used in gas chromatography to determine what? Retention time. Retention time to find the identity of the compound, right? Just now I said the retention time is, let's say, the TX, TY, TZ. So this is the retention time for TZ for this peak, TY for this peak, TX for this peak. This is the, so to identify. So okay, at TX I have a standard is showing me that there is X, so it should be X, something like that. So identity of the chemicals. In gas chromatography, compounds may be separated based on their molecular weight. Okay, their molecular weight. So the higher the molecular weight, it will take longer time to go out from the column because it is heavy. If it is smaller or lower molecular weight, it will go out faster because it can travel fast, right? Because it has a lower mass. The smaller the molecular weight, it will go detected. Okay, so a gas chromatography analysis was performed on a mixture of 1 hexanol, 1 octanol, 1 heptanol, 1 pentanol. Which of the peak is X? X represents what? Out of this hexanol, octanol, heptanol, pentanol, it is what? All this actually is telling that this is alcohol. All means alcohol. All right. So alcohol, and also that means it has a OH group in it. That is all. But I think we haven't studied the organic chemistry. But for now, we know that methane, ethane, propane, butane, pentane. Do we know that? I'm assuming that you know it. Okay, so let's say that pentane, we have methane, ethane, propane, butane, pentane. Which one is the lowest? Pentane is the lowest because pentane, because in Latin we count like mono, di, tri, tetra, hexa, hepta, penta, right? So that way, pentane means 5, hexa means it has 6 carbon, hepta means it has 7 carbon, octa means it has 8 carbon. Nonen and then nona and deca. So these are the 1, 2, 3, 4. In this way we can okay. another thing. Oh, so many things. So these type of things are coming. Okay, sorry. I mean, penta means 5, hexa means 6, hepta means 7, octa means 8. So since in gas chromatography it depends on the molecular weight of the component, right? What do you think that this X is going to be? Any idea? Oh, it's given already. But okay, let's say that X, Y, this is Z, Z. This is your Menti question. So what do you think this Z is and why it is short? Can you please answer? 2, 4, 6,
Because
8.
it's the heaviest.
Okay. Is the heaviest. Good. It is the heaviest. That is why it is coming out the last one, because time, the arrow showing that time is increasing. So if it is 5 minutes, it should be 6 minutes, 7, 8. So in this way, oh, is it confusing? Because 5, 6, 7, 8 pentahexa. If it is a 1 minute, it is 2 minutes, it is 3 minutes, it's 4 minutes, right? Because time is going this way up, increasing. So Z is the heaviest and it is lower, I mean, it has a lower amount in the mixture. So it should be octanol. Z should be octanol. So what is X then? It is hexanol, right? It should be pentanol. It should be hexanol, it's heptanol, and is octanol. Z is octanol. So X is hexanol. Question 13 says that some groups of bacteria produces volatile fatty acid, and these fatty acids can be identified using gas chromatography by comparison with a control chromatogram known standard. Fatty acids of the bacteria, identify the fatty acids can be determined by measuring their retention time, because if it is X, if it is Y, right? So how do we know that if it is what is what? By the retention time. The retention time, if it is 1 minute, 2 minute, 3 minute, 4 minute, based on the retention time, we will be able to identify which is what. The temperature of the column, no, temperature of the column is same for all of them. What is the difference between them? Only the time they are eluted. Eluted means they come out, go to and the detector detects it. So that is the eluted time. The flow rate of the carrier gas does not matter. The flow rate of carrier gas will always carry all of them equally. It does not mind, or the gas actually, in fact, the carrier gas is inert, is chosen so that it does not have any influence on those compounds. So it's carefully chosen. The area under the peaks. Area under the peaks is for what? Just now we say the amount. The area is this one. The area under the peak is to find out the amount, right, or the concentration of the component inside. So it is not to identify only by the retention time. Question number 14 says an athlete provided a urine sample to be tested for a steroid. Steroids sometimes the performers, the athletes, the performers, they usually take to increase their, productivity. And this is sometimes used. These are the things that used as a drug and is banned. The sample and the steroid standard were treated and then analyzed by gas chromatography. Below the chromatogram was found, and so this is the standard steroid mixture. All right, this is standard steroid mixture, and this is the sample from the athlete. This is the steroid mixture. We do the same, a mixture of different steroid, 4 steroid, nandrolone, nonandrosterone, strandazolol, and whatever another name. So this 4 is a mixture of these 4. I take and I inject it in the gas chromatography, and I wait for maybe 10-15 minutes and to come to know the time that it comes out, right? And then I took the urine sample from that athlete, and I run the urine sample same. You need to prepare the urine sample. It's not that you can take the urine and put it in the machine. No, you have to do something on the urine sample to prepare the sample so that the machine can actually read it. So that urine sample was prepared as a sample, urine was prepared as a sample and then run at exactly same column inside the machine, right? We saw the GC inside the machine, there is a column and we need to inject it, the sample at some temperature, same thing, everything is same. And we found that the elution or the peaks from the samples of athlete urine is I am getting one at 1.5. This is 1.5. Another one I got around 2.8, 3.3 or 3, no, 3.3 maybe, around 4.2, 4.3, one is at 5. One is something 6.7 maybe and 6.2. So this way I find many different peaks. Out of them, if there is any, if the athlete took really any steroid or not. So from here we see that it is one steroid at 2, peak number 2. There is no at peak number 2. So this nonandrolone is not in the sample. But, and then I see one is at 3.4 or let's say 3.5, right? We do not have a 3.5, is it? Do we have a 3.5? We don't have a 3.5. We have a 3.2 maybe, this one. Okay. We have here. But why somewhere it is smaller, somewhere it is bigger. See? So draw. So it is 3 point something. It is not exactly the same thing, but at 5 there is 1, and it is matching the same at here. So it's transolol, and then it is at one is a 7 point something, which is we don't have any peak here. So only this transolol is in the urine sample, so that athlete was complicit, and he or she actually took some kind of steroid, and he or she will be banned later on. Question 15 says a mixture of methanol and propanol was analyzed by gas chromatography. The concentration of methanol in this mixture was 80%. One on gas chromatography, the peak for the methanol will have a lower retention time or a higher retention time. What? So interestingly, the figure is missing here. Okay, let me just draw it quickly. So this is x-axis, this is y-axis, and then methanol 80%, propanol 20%. So this is methanol 80%, propanol. I don't want to delete all. Propanol 20%. So something like that. Okay. So this is 80%. And that is why it is too fat. You see, the peak is too fat because it is 80% altogether, and this is 20%. So it is a bit slimmer, right? So yeah. So the lower the peak for the methanol will have, this is methanol, MET, methanol, and this is propanol. Propanol, I put PRO, this propanol, yeah, you know, understand. So this is the time is increasing. So propanol is methane, ethane, propane. So there is 3 carbon here. And that is why I put it further down the time scale, because it will take longer time to elute. And the answer is correct, the lower retention time and higher area under the peak. So methanol is coming out faster, so it has a lower retention time. It does not stay longer there in the column, right? So that it will come out faster, and then it will have a higher retention time. Okay, so just hold on for a second. I go and make some tea for myself. You may as well go for some tea and make yourself comfortable. 2 minutes break. Okay, I'm back. And we are going for the past exam question. There is nothing much actually to talk. Yeah, it is almost everything is discussed here. So for the first question, it says the paracetamol is commonly used as painkiller, right? Or Panadol actually, the main component here in Malaysia, we call it paracetamol, Panadol. Okay, is a painkiller. Students use thin layer chromatography to analyze the paracetamol for the stationary and mobile phases used for this analysis. The RF of paracetamol is 0.4. Okay. On the diagram of a TLC plate below, use a horizontal line to mark the spot where paracetamol would appear in such an analysis. So show your working. So if it is a 0.4 and if the solvent front reaches to 5, right? If it were reaches to 10, I would have here. At 4, I would have at 4 had the solvent font reached to 10. But since it is only until 5, it will be here. Question number B says that another compound, 4-aminophenol, absorb less strongly than paracetamol onto the stationary phase on this TLC plate. Predict whether this RF value for 4-aminophenol in this analysis is greater or smaller than that paracetamol. Give a reason of your choice. If 4-aminophenol absorb less strongly than paracetamol, then what will happen? It does not get attracted to this stationary phase that much, less so of paracetamol, right? Less than paracetamol, it is attached. So what will happen is, if it is paracetamol, it will go higher, maybe at 3, maybe at 4, maybe at 5, we do not know where. So it will go more than that, and that is why it will have, the retention factor is higher. Okay, it will have a higher retention factor, and because it does not get attached to this stationary phase. Question number 2. Malic acid and lactic acid are two organic compounds that contribute to the characteristic taste of wine, and two samples of wine, sample 1 and 2, were analyzed by thin layer chromatography using a polar stationary phase. So the stationary phase is polar now. Okay. Reference samples of lactic acid and malic acid were also spotted onto the plate. The chromatogram obtained is shown below. This is standard lactic acid. We put here standard lactic acid, and then standard malic acid. Just 1 second, yeah. Oh, okay. So this is, I'm taking malic acid and lactic acid, two different two different components we have taken. And then I put sample, wine sample 1, wine sample 2, different wines I put here. So sample wine gives us a value here, and wine 1 gives us 2 values. So it's corresponding to this malic acid, but it does not have any malic acid. Sample 2, the wine number 2 does not have any malic acid, but sample 1, it has a lactic acid. Both of them has lactic acid, but only sample 1 has both of them and the acids in it. Sample 2 does not have both, only one. Okay, question number 3. The following chromatogram of a standard mixture containing 4 drug compounds analyzed by high performance liquid chromatography HPLC. Okay, MDMA, methamphetamine, amphetamine, and methaketamine, all those bad things. And then on the HPLC we tried, and we found that A, B, C, D, right? So A is amphetamine, B is methamphetamine. Oh, here State which compound ABCD is most polar if a non-polar stationary phase was used to separate 4 drugs. If the stationary phase was non-polar, then which of them is most polar? So if it is non-polar, it will stick to the stationary phase, non-polar. A comes out very fast. It does not stay. Just 5 minutes it comes out, but D stay to until 10 minutes. So D should be most which compound is most polar? So D is most non-polar and A should be most polar, right? Because A does not stay there on the non-polar stationary phase. It does not stay, it just come out. So it is the most polar compound. And this sample was collected from a illegal drug laboratory. We found a mixture of different drugs in that laboratory, and then we do the analysis on the drugs, and we found these are the chromatogram for the unknown samples, the mixture of different drugs. But we already have the references, or you may say that we have the standard references with us from the beginning, so that we can find out that A, B, C, D all together, right? Okay, all right, A, B, C, D. So in that drug laboratory, what is there present? A is at 5 point something, B is around this is 6 point something, C is at 7, let's say, or 7 point something maybe. So we see, and D is at 12, 13, something like that. So at between 5 to 10, I have only here, this is around 7. So in that sample, C should be there. So it should be C. And we do not know what is this, because in the standard, I do not have here at this time any peak. So I cannot say what is this one. But this one I can find in the standard sample, which is D. So this should be D. And these two also I cannot find. I mean, we do not know what is this, because we do not have a standard for these two. Okay, so here, I mean, what I just mentioned here, you should have to write in your Word. And this is the thing that we have done in the class. I'm not going through it. Okay, so I think this is pretty much same thing that you have done. Okay, question number 5. A forensic chemist wants to test the accuracy of gas chromatography that is to be used for the analysis of blood alcohol content, right? A blood sample may contain a number of volatile compounds that can interfere with the identification and measurement of ethanol in the blood. A sample containing a mixture of ethanol and several other volatile chemicals was injected into the gas chromatography, the chromatogram. The following chromatogram was obtained, right? This is different for chromatogram where it obtained. Here is that descriptive question. You have to come up with the answer. I'm going to the here. The following calibration graph was constructed using simulated and standard blood alcohol samples ranging in a concentration from 000 to 0.4 percentage, right? milliequivalent per volume. It should be, so it's MEQ. It should be okay. So each standard was run through the chromatography column, and the area under the peak produced at a retention time of 0.9 minute was measured. The blood alcohol content of a car driver was determined using the chromatographic technique, determine the percentage of mass per volume, actually, okay, mass per volume of alcohol, or weight per volume. Actually, this is the same thing, of weight per volume of alcohol in the driver's blood if the peak area at a retention time of 0.9 minute was found to be 110,000. Yeah. Okay, so the question is telling us that the driver's blood, here we found the alcohol, right, in the blood, and then how much was the alcohol in the blood? We have to find out by doing some standard sample testing. First of all, we want to quantify. We don't want to just analyze that, whether identify. We don't want to just identify, but now we want to quantify. Identify means we want to know the identity. We already know the identity is ethanol, so we don't have to identify, but quantify, that means how much of alcohol was there. So the blood sample was diluted. We took the blood from the driver, we diluted it, and then this diluted sample was then run into that same instrument, same machine, where there were a standard sample testing was done already. Standard run already done. Standard, we made 4 different standard we made, okay. 0.000, that means there is no alcohol in that standard, to 0.4%. So here, when we do the 0.00, no alcohol, so of course we will not get any peak. So there is the peak means no peak means 0. And then we took another sample with, we dissolved 1% or 0.1% of alcohol in their sample. So we found a peak around here and we call it 1%. Then we found another peak for the sample that we prepared, 2%. So this is a standard. This is how we produce the standard. Okay. So 0, 1, 2, 3, 4, 5 point, of course, 0.1, 0.2, 0.3, 0.4, 0.4. All 4 samples we prepared, and 0 was, there was nothing, only water. And then the peak area of that samples we measured and we put it against the graph of percent of ethanol and peak area. So this is the data we found. This is the graph we found. All right. And then now I do not know in the blood how much, we just diluted it, but we do not know how much of that alcohol is there. But all these 5 samples, we know how much alcohol in my 5 samples now. Now I'm doing the blood analysis and I got a peak of around 110,000. 110,000. So here it should be the peak. I got a peak here because this is 110,000, right? This is 110,000. This line means 110,000. So this is where I got the peak. Now I draw a line on our standard curve, and then we drop it down to the x-axis. Excuse my drawing. So we drop a line here and we find the line to be touching this part, which is 0.21. 0.21 mass over volume percentage of ethanol in the blood. This is how we will find. Okay, this we will find. This is the mass over volume in the blood the driver has in his blood. Or sorry, this one is, let me just check once again. 0.21, 2223. No, is every unit is 0.02, right? Like hold on, let me show you. So this is 0, we know this is 0. This is 0.2, 0.02, sorry. This is 0.04. This is 0.08. 6. This is 0.08. And then this is 0.1. So every unit, this unit, right? This unit is 0.02. So for that's why it will be 0.22. 0.22 mass over volume for this case. All right. So this is it for today. Anybody has any question? No? And I think I was telling that I will discuss about the polar and non-polar thing. So polar means it has two different poles. Simple way of expressing, but it does not express. It does not define, right? Sometimes students do this way. What is polar? It has poles. It doesn't define. Two poles means it can separate into different charge, positive and negative charge. It can differentiate. So water is a polar. Why? Because water can dissociate and produce hydrogen and hydroxyl ion. Methanol is polar because CH3OH, because it can produce a polar ion, hydroxyl and positive charge. So that is why sodium chloride is polar, because sodium chloride, if it is in the water, it will dissociate and produce charges. Of course, for water, it is delta. We call it delta charges because it is a small amount. It's not 100% positive negative, but for sodium chloride, it is totally positive and negative charge. And that is why sodium chloride is a very good conductor, electricity conductor, but water is not a good conductor. Okay, water does not conduct much electricity. But do not try. Don't put the electric wire in the water and don't get wet in that water. You will be electrocuted. It does not conduct electricity, means not that much, but it still does. So be careful. Okay, so this is why, when the solvent like ethanol, methanol, water, sodium chloride solution, all those things are polar because they are able to be separated into charge. Non-polar, they are not able to be separated. Like non-polar is ammonia, or it is benzene, okay, or butanol, or higher alcohol like octanol, nonanol, those types. And carbon tetrachloride, oh, the easiest is carbon tetrachloride. So it does not get separated, charge separation, it does not get charge separation. So it is a non-polar. Cyclohexane. Cyclohexane. This is also non-polar. Then another thing is chloroform. CH3, chloroform is CHCl3, I think. I forgot. Yeah, so these all things, these are the solvent. That means they are in liquid form, so they do not get separated by charge. But these water, methanol, ethanol, propanol, butanol, they always get separated. They are able to be separated into charge. Why they are not separated and why they are separated, maybe they have a question, and it will take some other chemistry knowledge. Probably we'll discuss when you go to degree, if you take chemistry class, of course, because of their electronegativity differences. Okay, and also because due to their bonding. So we'll discuss later on probably, but I hope that it will be enough for you to understand that they get separated into charges. That's why they are polar. When they do not get separated into charges, they are not polar. All right, so any other question anybody has? If no question, then I'll see you next Monday for the next tutorial lecture. That lecture will be on probably UV. I forgot. But all the best. Take care. Have a nice weekend. Stay safe.